When we discuss the quantum nature of charge, we also mention that it does not play any role in the description of macroscopic charge attained by a body. Therefore, in the classical theory of electromagnetism we can apply the phenomenological description of charge, where the distribution of macroscopic charge in space is regarded as a continuous charge distribution. Such a continuous distribution of charge is described by the scalar-valued vector function called charge density. For a given point determined by a position vector r with respect to a reference point O, the charge density ρ gives the density of the charge in that point. However, the strict interpretation of the density of charge depends on the geometry of the charge distribution. If we consider a charge-thin wire, we study a one-dimensional problem, where the wire can be described by a space curve C. In this case the charge density describes the charge distribution along the wire, and the infinitesimal charge dq distributed along an infinitesimal length L of the wire is given by the charge density lambda times dl, where lambda is a function of the length L measured along the curve C. Here the charge density lambda along the curve C is defined by the derivative of the charge q with respect to the length L, measured from a given reference point on the curve. By virtue of this definition, the SI unit of the charge density is equal to coulomb per meter. We can obtain the total charge q attained by the wire, if we integrate the charge density lambda along the curve C. Another typical problem in electromagnetism is the study of the charge distribution over the surface of bodies, the plates of capacitors, or interfaces between different materials. In such cases we apply a mathematical description of the surface S, and the charge density describes the charge distribution over the surface. The infinitesimal charge dq distributed over the infinitesimal surface or area element ds is given by the product of the charge density sigma and the surface element ds, where sigma depends on the coordinates u and v describing the position of the surface element on the surface S. As a result, we define the surface charge density sigma by the derivative of the charge q with respect to the surface area S, and the SI unit of the charge density is equal to coulomb per square meter. In order to obtain the total charge q attained by a surface, an interface or a plate, we need to integrate the charge density sigma over the surface S. The most general problem considered in electrostatics is the study of charged bodies in the three-dimensional space. In such cases, we deal with charge distributed throughout the volume V of a body, and the spatial charge density ρ describes the charge distribution within this volume. Then the infinitesimal charge dq distributed in the infinitesimal volume element dv is given by the spatial charge density ρ times the volume element dv, where the charge density depends on the position vector or describing the position of the volume element with respect to a reference point O. As a result, we define the spatial charge density ρ by the derivative of the charge q with respect to the volume V, and the SI unit the spatial charge distribution is equal to coulomb per cubic meter. The integral of the charge density ρ over the volume V gives the total charge distributed throughout this volume. If we want to determine the electric field in a given point P created by the macroscopic charge distribution Q, we can proceed as follows. First we apply the formula obtained for the electric field of a point charge to compute the contribution to the electric field in the point P from an infinitesimal charge in an arbitrary point within the macroscopic distribution of the charge. Then we integrate these contributions over the whole volume of the charge distribution, which provides the net electric field in the point P created by the total macroscopic charge. The electric field E of a point charge Q in the point P is equal to 1 over 4 pi times epsilon naught, times the charge Q divided by the square of the distance r between the point charge and the point P, times the position vector r pointing from the point charge to the point P divided by the distance r. If the source of the field is the infinitesimal charge dq approximated by a point charge, then its contribution dE to the electric field in the point P is given by 1 over 4 pi times epsilon naught, times the charge element dq divided by r squared, times the vector r divided by its length. Here the vector r points from the charge element to the point P. In order to determine the electric field E in the point P created by the total amount of the charge Q, we integrate this expression with the infinitesimal charge dq over the whole charge Q. This process can be interpreted as the continuous version of the principle of superposition for electric fields. Then the electric field E in the point P is given by 1 over 4 pi times epsilon naught, times the integral of 1 divided by r squared, times the vector r divided by its length with respect to the charge over the whole macroscopic charge Q. For the sake of completeness, we express the position vector r in the integral as the difference between the vectors rp and r prime, pointing from the reference point O to the point P in the infinitesimal charge dq respectively. The electric field E in the point rp is given by this integral, where the independent variable q in fact is a function of the position vector r'. Therefore the independent variable of the integrand can be changed from the charge q to another variable related to the geometry of the problem. Let us see how to proceed with it in the 1, 2 and 3-dimensional cases. We have seen that the infinitesimal charge element dq along a charged wire can be written as the linear charge density lambda times the infinitesimal length dl measured along the curve C. As a result, the electric field E created by a charged wire is equal to 1 over 4 pi times epsilon naught, times the line integral of the charge density lambda divided by r squared, times the vector r divided by r with respect to the length L along the curve C. Here the line element dl can be expressed in the terms of the vector r pointing from the charge elements along the curve to that point, and we can perform the integration with respect to the coordinates of the vector r. For the electric field created by charged surfaces, the infinitesimal charge element dq is given by the surface charge density sigma times the infinitesimal surface element ds. Then the electric field E created by a charged surface S is equal to 1 over 4 pi epsilon naught, times the surface integral of sigma divided by r squared, times the vector r divided by its length, over the surface S. Here the surface element ds can be expressed in the terms of the position vector r, and the independent variable of the integrand can be changed to the coordinates of the vector r. For a spatial distribution of charge, the infinitesimal charge dq is given by the spatial charge distribution ρ times the infinitesimal volume element dv. Then the electric field E created by the charge distributed in the volume V is equal to 1 over 4 pi epsilon naught, times the volume integral of ρ divided by r squared, times the vector r divided by its length, over the volume V. Here the volume element dv can be expressed in the terms of the position vector r, and the independent variable of the integrand can be changed to the coordinates of the vector r. In the first example for the application of charge density we determine the electric field created by an infinitely long thin straight uniformly charged wire. We approximate the wire with an infinite line, along which the charge is uniformly distributed. The figure shows a section of the positively charged line and the point P where we want to determine the electric field strength. We choose the closest point of the line to the point P as the origin of a Cartesian coordinate system, where the x-coordinate measures the distance along the line. Here the distance of the point P from the line is given by the y-coordinate. For a uniform charge distribution along the line, the infinitesimal charge or the charge element dq in a small portion of the line at the distance x from the origin is equal to the product of the constant charge density lambda and the line element dx measured along the line. Then the contribution dE of the charge element dq to the magnitude of the electric field E is given by 1 over 4 pi epsilon naught, times the ratio of lambda times dx to r squared. Here r is the distance of the line element dx from the point P, which is equal to the square root of x squared plus y squared. The components of the vector dE in the Cartesian coordinate system can be seen in the figure. If theta is the angle measured between the y-axis and the direction of the line element dx seen from the point P, then the x component of the vector dE can be written as minus dE times sine theta, and its y component is equal to dE times cosine theta. In order to obtain the components of the electric field strength E, we need to integrate the contributions of the charge elements to the field along the line. The x component of the electric field E is equal to the integral of dEx, which can be written as minus the line integral of sine theta with respect to the magnitude of E along the infinite line. Similarly, the y component of the electric field E is equal to the integral of dEy, which can be written as the line integral of cosine theta with respect to the magnitude of E along the infinite line. Since the geometry of the infinite line is reflection symmetric about the origin, for each charge element on the left-hand side of the origin there is a corresponding charge element on the right-hand side. Then the electric fields created by these charge elements on both sides have the same magnitudes. Their y components point in the same direction but their x components point in opposite directions. As a result, these infinitesimal contributions to the net electric field cancel each other out in the x direction. That is, the x component of the electric field strength vanishes and it has only a y component. Since the contributions of the charge elements on the left and right-hand sides of the origin are the same, it is enough to take 2 times the integral of the contributions in the y direction over the half of the x-axis. Now we see that the magnitude of the electric field E is equal to its y component, and the substitution of the result obtained for Ey into this formula gives 2 times the line integral of cosine theta with respect to the magnitude of E from the origin of the line to infinity. We have already determined the differential of the magnitude of E, which we can insert into this equation. Then the magnitude of the electric field can be written as lambda over 2 pi epsilon naught, times the integral of cosine theta over x squared plus y squared with respect to x from 0 to infinity. Here cosine theta can be expressed in the terms of the Cartesian coordinates. We see in the figure that the distance x of the line element dx from the origin is equal to the distance y times tangent theta. If we take the differential of this equation, we see that dx is equal to the ratio of y to the square of cosine theta, times d theta. Then dx over x squared plus y squared is equal to the ratio of y times d theta to the square of cosine theta times x squared plus y squared. Since x is equal to y times tangent theta, we have the ratio of y times d theta to y squared times the square of cosine theta, times the square of tangent theta plus 1. After simplifying this expression, we obtain d theta divided by y times the square of sine theta plus the square of cosine theta. Since the square of sine theta plus the square of cosine theta is equal to 1, we obtain that dx over x squared plus y squared is equal to d theta divided by y. If we substitute this result into the integral, the magnitude of the electric field can be written as lambda over 2 pi times epsilon naught times y, times the integral of cosine theta with respect to theta from 0 to pi divided by 2. By performing the integration, we obtain lambda over 2 pi times epsilon naught times y, times the primitive function sine theta evaluated at the lower limit 0 and the upper limit pi over 2. The evaluation gives lambda over 2 pi times epsilon naught times y. Therefore, the magnitude E of the electric field created by a uniformly charged infinite line at any point with the distance y from the line is given by the charge density lambda divided by 2 pi times epsilon naught times the distance y. The electric field points radially away from the positively charged line. This formula shows that the magnitude of the field is inversely proportional to the distance from the line, that is, the electric field of a point charge falls off faster at large distances than the one created by the uniformly charged infinite line or wire. The next example is rather similar to the previous one, where we determine the electric field created by a uniformly charged thin ring on its axis. We suppose that the thickness of the ring is much smaller than its radius and approximate the ring with a circle, along which the charge is uniformly distributed. The figure shows a positively charged circle with the radius capital R and the point P on its axis where we want to determine the electric field strength. We choose the center C of the circle as the origin of a Cartesian coordinate system, such that the z-axis is perpendicular to the plane of the circle. Here the distance of the point P from the plane of the circle is given by the z-coordinate. For a uniform charge distribution along the circle, the infinitesimal charge dq in a small line element dl of the circle at its intersection with the y-axis is equal to the product of the constant charge density lambda and the line element dl. Then the contribution dE of the charge element dq on the circle to the magnitude of the electric field E is given by 1 over 4 pi times epsilon naught, times the ratio of lambda times dl to small r squared. Here small r is the distance of the line element dl from the point P, which is equal to the square root of capital R squared plus c squared. The components of the vector dE in the Cartesian coordinate system can be seen in the figure. If theta is the angle measured between the z-axis and the direction of the line element dl seen from the point P, then the y component of the vector dE can be written as minus dE times sine theta, and its z component is equal to dE times cosine theta. In order to obtain the components of the electric field strength E, we need to integrate the contributions of the charge elements to the field along the circle. The y component of the electric field E is equal to the integral of dEy, which can be written as minus the integral of sine theta with respect to the magnitude of E along the circle. Similarly, the z component of the electric field E is equal to the integral of dEz, which can be written as the integral of cosine theta with respect to the magnitude of E along the circle. Since the geometry of the circle is rotational symmetric about its axis, for each charge element on one side of the axis there is a corresponding charge element on the other side. Then the electric fields created by these charge elements on both sides have the same magnitudes. Their z components point in the same direction, but their components parallel with the plane of the circle point in opposite directions. As a result, these infinitesimal contributions to the net electric field cancel each other out in the y direction. That is, the y component of the electric field strength vanishes and it has only a z component. Now we see that the magnitude of the electric field E is equal to its z component, and the substitution of the result obtained for Ez into this formula gives the integral of cosine theta with respect to the magnitude of E along the circle. We have already determined the differential of the magnitude of E, which we can insert into this equation. Then the magnitude E of the electric field can be written as 1 over 4 pi times epsilon naught, times the line integral of cosine theta times lambda over capital R squared plus c squared with respect to the length L along the circle. Here cosine theta can be expressed in the terms of the Cartesian coordinates, which is given by the ratio of the distance z to the distance small r. That is, cosine theta is equal to z over the square root of capital R squared plus c squared. If we substitute this result into the integral, the magnitude of the electric field can be written as 1 over 4 pi times epsilon naught, times z over capital R squared plus c squared to 3 over 2, times the integral of lambda with respect to the length L along the circle. We immediately see that the integral is just the integration of the charge along the circle, which gives the total charge Q distributed along the ring. Therefore, we obtain the magnitude E of the electric field created by a uniformly charged ring with the radius capital R and a total charge Q and a point on its axis at the distance z from the center of the ring, which is given by 1 divided by 4 pi times epsilon naught, times Q times z divided by capital R squared plus c squared to 3 over 2. The electric field of the positively charged ring along the axis is parallel with the axis itself and points outward from the plane of the ring. This formula also shows that the magnitude of the field is inversely proportional to the square of the distance from the ring, if the distance e is much greater than the radius capital R of the ring. Roughly speaking, the electric field created by a charged ring along its axis looks like the one of a point charge with the same total charge at distances far from the ring. After studying electric fields due to charge uniformly distributed along a line or a curve, we present the electric field generated by surface charges. In the first example, we determine the electric field around a uniformly charged plate or plane sheet extending to infinity. We start with a plate with a finite extension L, and we compute the electric field in the point P on the z-axis of the Cartesian coordinate system attached to the middle of the plate such that the x and y axes are parallel with the edges of the plate. We assume that the distance z of the point P from the plate is much smaller than the length L of the sides of the plate. For a uniform charge distribution over the plate, the charge element dq over any area element ds is equal to the constant surface charge density sigma times the area ds. If we partition the plate into infinitesimally thin strips with the length L and the infinitesimal width dy, then the area ds element can be written as L times dy, and the uniformly distributed charge over each strip is given by sigma times L times dy. We consider the strips with the infinitesimal width as lines with the linear charge distribution lambda, given by the ratio of the charge element dq to the length L of the strips. Since the charge distributed over each strip is equal to the surface charge density sigma times the length L times the width dy, lambda can be written as sigma times dy. Now we determine the electric field created by the infinitesimal charge which is uniformly distributed along a given strip at the distance y from the x-axis. Since the strip is very long compared to the distance r of the point P from the strip, we can apply the result obtained for a uniformly charged infinite line. Then the contribution dE of the charge element dq distributed along a line to the magnitude of the electric field is given by 1 over 2 pi times epsilon naught, times the ratio of the linear charge density lambda to the distance r. Here we already expressed the distance r as the square root of z squared plus y squared. By substituting the product of the surface charge density and the infinitesimal width dy into lambda, we obtain 1 over 2 pi times epsilon naught, times sigma times dy divided by the square root of z squared plus y squared. The components of the vector dE in the Cartesian coordinate system can be seen in the figure. We obtain the components of the net electric field E in the point P by performing the integration of the contributions of the strips over the whole plane. If theta is the angle measured between the z-axis and the direction of the middle of the strip seen from the point P, then the y component of the magnitude of E is the integral of dEy, which is equal to minus the integral of sine theta with respect to the magnitude of E. Similarly, we obtain the z component of the magnitude of E by performing the integration of dEz, which can be written as the integral of cosine theta with respect to the magnitude E. Since the geometry of the sheet is symmetric about the x-axis, for each strip with their charge element dq on one side of the axis there is a corresponding strip with the same charge element on the other side. Then the electric fields created by these charge elements on both sides have the same magnitudes. Their z components point in the same direction but their y components point in opposite directions. As a result, these infinitesimal contributions to the net electric field cancel each other out in the y direction. That is, the y component of the electric field strength vanishes and it has only a z component. Then the magnitude E of the electric field is equal to its z component, which is given by sigma times z over 2 pi times epsilon naught, times the integral of cosine theta divided by the square root of z squared plus y squared with respect to y from minus L over 2 to plus L over 2. Here cosine theta can be expressed in the terms of the Cartesian coordinates, which is given by the ratio of the distance z to the distance r. That is, cosine theta is equal to z over the square root of z squared plus y squared. As a result, we have sigma times z over 2 pi times epsilon naught, times the integral of 1 over z squared plus y squared with respect to y from minus L over 2 to plus L over 2. By performing the integration, we obtain sigma times z over 2 pi times epsilon naught, times the primitive function 1 over z times tangent y divided by z, which we evaluate at the lower limit minus L over 2 and the upper limit L over 2. This formula already gives the electric field strength E on the z-axis erected in the middle of the charged plate with a finite size. However, we are interested in the electric field of a uniformly charged infinite plane and we take the limit of this expression. That is, we determine sigma over 2 pi times epsilon naught times the limit of 1 over the tangent of y divided by z, which we evaluate at minus L over 2 and L over 2 as L tends to infinity. The limit of this expression is equal to sigma over 2 pi times epsilon naught times the difference of pi over 2 obtained at the upper limit of the integration, and minus pi over 2 obtained at the lower limit of the integration, that is pi over 2 plus pi over 2. By simplifying the expression we obtain sigma over 2 times epsilon naught. Then we see that the magnitude E of the electric field is constant over and above the sheet, and it is equal to the surface charge density sigma of the infinite sheet divided by 2 times epsilon naught. The direction of the electric field created by the positively charged sheet perpendicular to the plane of the sheet and points outward on both sides of the sheet. Then we can conclude that the electric field is homogeneous or uniform around a uniformly charged infinite sheet. In the second example illustrating electric charge distributed over a surface, we determine the electric field around a uniformly charged disk, which can be applied to derive the result obtained for the uniformly charged infinite plane sheet by extending the radius of the disk to infinity. For a uniformly charged disk with the radius R, we will compute the electric field in the point P on the z-axis of the Cartesian coordinate system attached to the center of the disk. Then the distance of the point P from the disk is given by the coordinate z. Since the distribution of the positive charge is uniform over the disk, the charge element dq over any area element ds is equal to the constant surface charge density sigma times the area ds. Let us partition the disk into thin rings with the radius r and the infinitesimal width dr. For the sake of brevity, we only use the letter r for the radius of the disk denoted by small r and its differential, as opposed to the radius capital R of the disk, where we always indicate that it is a capital letter. Then the area element ds of each ring is the difference of the areas of the disks with the radii r plus dr and r. That is, ds is equal to pi times the square of r plus dr, minus pi times r squared, which is equal to pi times r squared plus 2 pi times r times dr, plus pi times dr squared minus pi times r squared. Here we can neglect the term pi times dr squared, which is second order in the infinitesimal width dr of the ring. Then we can approximate ds with the expression 2 pi times r times dr. Thus we have partitioned the disk into rings with the radius r and the width dr, which have the infinitesimal area 2 pi times r times dr. As a result, the charge element dq over each ring is given by 2 pi times the surface charge density sigma, times the radius r of the ring, times the width dr of the ring. Now we determine the electric field along the axis of the disk, which is created by the infinitesimal charge uniformly distributed along a given ring. For such a geometry we can apply the result obtained for a uniformly charged ring. Here we show the contribution dE of the charge element dq distributed along a ring to the magnitude of the electric field in the point P located at the distance of the square root of r squared plus d squared from the ring. The contribution dE is parallel with the z-axis and points outward for the positively charged disk due to the axial symmetry of the charge distribution. We also have seen that the magnitude of dE is given by 1 over 4 pi times epsilon naught, times the ratio of the distance z times the charge element dq to r squared plus c squared to 3 over 2. By expressing the charge element in terms of the surface charge density, we obtain 1 over 4 pi times epsilon naught, times 2 pi times sigma times r times dr divided by r squared plus c squared to 3 over 2. The magnitude E of the electric field in the point P on the axis can be determined by integrating the contribution dE of each ring over the whole disk. This gives sigma times z over r2 times epsilon naught, times the integral of r divided by r squared plus c squared to 3 over 2 with respect to r from 0 to capital R. We can change the variable of the integration by introducing the variable u for the expression r squared plus c squared, where the differential du is given by 2 times r times dr. The lower limit of the integration becomes z squared, and its upper limit will be the square of capital R plus c squared. As a result, we have sigma times z over 4 times epsilon naught, times the integral of u to minus 3 over 2 with respect to u from z squared to the square of capital R plus c squared. By performing the integration, we obtain sigma times z over 4 times epsilon naught, times the primitive function u to minus half divided by minus half, which we evaluate at the upper limit of the square of capital R plus c squared and at the lower limit z squared. Then the result is equal to minus sigma times z over 2 times epsilon naught, times 1 over the square root of the square of capital R plus c squared, minus 1 over the square root of z squared. We can factor out 1 over z from the terms in the parentheses, and we get sigma over 2 times epsilon naught, times plus or minus 1, minus 1 over the square root of 1 plus the square of capital R divided by z squared. Here we use the plus sign in the first term in the parentheses if z is positive, that is if the point P is located above the disk, and the negative sign if the z is negative, that is if the point P is located under the disk. Since the problem is reflection symmetric about the plane of the disk, we only use the expression describing the field above the disk. Then we have determined the magnitude E of the electric field due to the uniformly distributed charge over a disk with the radius capital R and the point P on its axis at the distance c, and it is given by sigma times z over 2 times epsilon naught, times 1 minus 1 over the square root of 1 plus the square of capital R divided by z squared. The electric field strength E in the point P is parallel with the z-axis and points outward from the disk. If the radius capital R of the disk tends to infinity, that is the distance z is negligible to the radius capital R, then the second term in the parentheses becomes negligible, and the whole expression approximates sigma divided by 2 epsilon naught, as we expected. That is, the electric field around the axis of a large charged disk is uniform, and perpendicular to the plane of the disk. We can apply the result obtained for a uniformly charged infinite plane sheet to determine the electric field created by 2 uniformly charged infinite parallel planes. We assume that one of planes has the surface charge density sigma and the other one has minus sigma, that is the planes have the same amount but opposite charges plus q and minus q. First, we choose the point PL on the left-hand side, the point PB between the two planes and the point PR on the right-hand side where we examine the properties of the uniform electric fields due to the charged planes. Since the electric field E sub plus created by the positively charged plane points outward, it points to the left in the point PL, and points to the right in the points PB and PR. In contrast, the uniform electric field E sub minus created by the negatively charged plane points inward, therefore it points to the right in the points PL and PB, and points to the left in the point PR. We have already seen that the magnitude of the electric field due to a uniformly charged infinite sheet is equal to its surface charge density divided by 2 times epsilon naught. That is, the magnitudes of both the electric fields E sub plus and E sub minus are equal to sigma over 2 times epsilon naught. The only difference between these fields is that the field E sub plus points outward and the field E sub minus points inward. Now we can apply the principle of superposition for electric fields to determine the net electric field E created by both the charged planes. We start with the net electric field in the point PB located in the space between the planes. As the figure shows, both the electric fields E sub plus and E sub minus point in the same direction in that point. Therefore we can write that the electric field E sub plus is equal to the electric field E sub minus, and this relation holds everywhere between the planes. As a result, the superposition of the two vector fields is just the algebraic sum of their magnitudes, that is the magnitude E of the net field is equal to the sum of the magnitudes of E sub plus and E sub minus. If we substitute the equations obtained for E sub plus and E sub minus, this sum can be written as sigma over 2 times epsilon naught plus sigma over 2 times epsilon naught, which gives sigma over epsilon naught. By comparing the result with the fields E sub plus and E sub minus, we can see that the magnitude of the net electric field strength is 2 times greater than the fields created by the charged planes but it points in the same direction. That is the field E points from the positively charged plane towards the negatively charged one. If we consider the points PL and PR on the left and right-hand sides of the pair of the planes, we see that the electric fields E sub plus and E sub minus point in opposite directions. This fact can be expressed by the vector equation stating that the electric field E sub plus is equal to minus the electric field E sub minus outside the space between the planes. As a result, the magnitude E of the net electric field on those spatial domains is given by the difference of the magnitudes E sub plus and E sub minus. Then we have sigma over 2 times epsilon naught minus sigma over 2 times epsilon naught, which gives 0. That is, in the left and right hand side regions of the planes the electric fields E sub plus and E sub minus cancel out and the net electric field E vanishes. Then we can conclude that the electric field E is uniform in the space between two parallel uniformly charged infinite planes with the same but opposite charges. Its magnitude is equal to the surface charge density sigma of the planes divided by epsilon naught, and the field points from the positively charged plane towards the negatively charged one. The electric field E is 0 everywhere else. This result also holds for charged finite plates with the same size, provided the distance d between them is much smaller than their linear extension L. Here we can see a capacitor consisting of two metal discs with a given radius and an apparatus used to modify the distance between the two plates, so that one can study the homogeneity of the field between the plates for different distances.